Dear friend, here we are going to discuss a very good example for the calculation of deflection for a cantilever beam which is subjected with uniformly distributed load W throughout its length, and we need to find deflection at tip of this cantilever beam. Now this can be also shown through this pictorial representation. We need to find deflection at tip of this beam. This is the tip of this beam, which is designated with B, and fixed support is designated with A, and we need to find delta B. This is our main objective. This problem will be solved using unit load method. As you remember, the expression of unit load method for calculation of deflection, it is expressed as delta equal to m1 m2 dx divided by ei integral from 0 to L. Length of this beam is L, and this from 0 to L. This is the deflection, as we are going to calculate deflection at point B, which is expressed as delta B. So our main objective is to find delta B. For this, we have to find out M1 and M2. For now, we need to understand what is M1 and M2. M1 is moment at a section XX. At a section XX from point B, there is tip of this beam which is at a distance of x from B, and beam is loaded with entire beam, entire beam is loaded with uniformly distributed load UDL equal to W. Now M2 will be moment at a section XX, which is at a distance of x from tip of this beam when beam is subjected with point load of value 1, or you can say unity, at tip of this beam. This is the statement of M1 and M2. During solution of this problem, you will be able to understand very easily what is M1 and M2. Now, the problem statement is, this is the problem. Beam is loaded with UDL W, its length is L, and our objective is to find out deflection at point B, which is delta B. We have also wrote an expression for delta B as delta B equal to M1 M2 dx divided by EI integral 0 to L. And in this M1 and M2 I have explained with a statement what is M1 and what is M2. Now try to understand with a pictorial representation what is M1 here. The beam is this is the cantilever beam subjected with a UDL equal to W, span is L. Now we are taking a section XX that I have explained in a statement, and this section will be at a distance of X from this point P, this is tip of this beam, and we need to find moment at this section XX. This will be the moment will be designated as MXX, and it is nothing but M1. Our main focus will be to find out M1. Now this is the anticlockwise moment. Our assumption is what is our assumption? Assumption is anticlockwise moment will be negative. This is the load W which is acting throughout the length of this beam, and our main objective is to find out moment at section XX. So this is the loading area, loading part, and this is UDL. So MXX, or you can say M1 will be, this is the total load. What will be the total load? W multiplying with this load. This is the W, it will be in kilonewton per meter. This is the UDL, so load UDL multiplying with this length, it will give the total load WL, at section X, W into X, it will be the total load, and this load is acting at a distance of X by 2 from this section XX. This is the point load, and I mean total load, which is WX, acting at a distance of X by 2, half of this length. So multiplying with this X by 2, this is the total load. Total load is acting at a distance of X by 2 from this section XX. So moment will be WX square by 2, and anticlockwise moment is taken negative, so we will multiply with negative sign, so it will become minus. So minus WX square by 2 will be the M1. Now we can also represent M2 as per the statement. There will be a point load at the tip of this beam, then amount of this point load will be 1, and as you know, tip of this beam has been designated with point B, and our main objective is to find out a moment at a section XX, which is at a distance of X from point B. So we need to find out this moment MXX, nothing but M2, which is expressed in this statement. This is M2. M2 we can find out easily. The load acting at tip of this beam is 1, which is at a distance of X, so load multiplying with the distance will give us moment. So moment will be, since the moment is anticlockwise direction, so it will be minus 1 multiplying with amount of load 1, and distance is X, so M2 will be minus X, this M2. Now we need to put value of M1 and M2 in the expression, so that we will find deflection delta B. Now delta B will be 0 to L. In place of M1 we will put this one, in place of M2 we will put this one, minus WX square divided by 2, and for M2 it will be minus X dx divided by EI. Now it will be 0 to L WX cube divided by twice EI. 0 to L, we can take W divided by twice EI outside, W twice EI outside, integral 0 to L x cube dx. Integral of x cube will be x to the power 4. W divided by twice EI, it will be x to the power 4 divided by 4, ranging 0 to L. So hence delta B will be W to the power W divided by twice EI, x to the power 4 divided by 4, 0 to L. It will be W twice EI multiplying L to the power 4 divided by 4. It will be W L to the power 4 ATI delta B. Now delta B will be, as we have calculated here, WL to the power 4 ATI. This is the deflection at tip of this beam. Now we done with the calculation for deflection at point B with unit load method. In our later on lecture, like lecture 3, we'll calculate same deflection delta B for the same beam which is subjected with a UDL by another method like moment area method and conjugate beam method. I hope you have understood the entire concept, and if you want to revise our 4 method which I have used for the calculation for deflection for a point load for a cantilever which is acting at tip of a cantilever beam through 4 method: unit load method, strain energy method, conjugate beam method and moment area method. Thanks for watching. Keep sharing to your friends, your colleagues. Thank you so much.